As far as any kind of difference of means scenario is concerned, independent samples is really the default scenario. You would only use the paired sample methodology if you have evidence that your data are paired. Something like before and after measurements on the same set of individuals would certainly qualify, but if there's nothing there, if there is no connection between your two samples, you have independent samples. And as opposed to paired samples, where there you effectively combine everything together by treating the difference like it's the variable, here you keep everything separate. That's why there are two sample sizes, two sample means, two sample standard deviations. You keep everything separated out. The standard error is a little bit more complex than what we had before, but it's not too bad. The conditions for inference really apply individually to each sample size, although usually the two sample sizes are comparable. It's very rare to have one sample size large enough where you can apply the central limit theorem and having the other one be tiny. Usually either they're both tiny or they're both big enough to apply the central limit theorem. The way that you find the degrees of freedom is a little bit different. There are more complicated ways of doing it, and this is kind of an overly conservative way of estimating the degrees of freedom, but it's a lot easier to follow along with. The way that we're going to estimate the degrees of freedom is the minimum of n1 minus 1 and n2 minus 1. That's how our book does it, so that's how we're going to do it. The sampling distribution of x1 bar minus x2 bar would have a mean of mu1 minus mu2, standard error of that root, which we could estimate using s's instead of sigmas. The confidence interval is still the same general format that it was before of point estimate plus or minus critical value times the standard error. Here the point estimate is a difference of sample means. The critical value comes from a t-distribution, since this has to do with means rather than proportions, and then the standard error is that root. The test statistic is still the same general format as before, point estimate minus value from the null hypothesis divided by the standard error. The value from the null hypothesis is going to be 0. You could theoretically have other values there, but they would be extremely unorthodox. Our book doesn't even entertain that idea, so we won't either. Typically, if you're doing a test involving a difference in means with independent samples, it's to either look for evidence of a difference between the means or specifically that one of them is larger than the other. In either of those cases, that would involve a null hypothesis of mu1 minus mu2 equals 0. The confidence interval example, estimating the mean difference between the annual costs of private and public colleges. We have two tiny sample sizes, so since n1 and n2 are so small, we're going to assume both populations are normally distributed. And what I mean by n1 and n2, and I suppose going forward, subscripts of 1 and subscripts of 2 in general, the way I'm thinking about that is subscripts of 1 in the first row and subscripts of 2 in the second row, so 1 for private and 2 for public. If we want to construct a 95% confidence interval, first we'll have to get a critical value. Since this is a scenario where we have independent samples, it'll be the minimum of 11 minus 1 and 14 minus 1, which works out to eventually be 10, since that's really the minimum of 10 and 13. So the critical value comes from a t-distribution with 10 degrees of freedom, 95% confidence interval, so we need a 0.95 in the center, and we get a critical value of 2.228. There's the computation of the confidence interval, which is also there in the notes already. I broke off the standard error computation and did that by itself. You could do that all at once if you wanted to. That would be a lot of individual steps if you did it all at once, but that would still be the first thing that you'd have to do following the order of operations to simplify that root. In any event, you simplify the root, then multiply by the critical value of 2.228, and then you do the plus minus. Eventually you end up with 20.2 plus or minus 5.412, and then you get the endpoints. The interpretation of the confidence interval is a little more complex because there are two parameters. If you take the context out, I'm saying that we are 95% confident that mu1 is between $14,788 and $25,612 more than mu2. To write out those parameters, in each case the type of number is a mean, and the specification part is annual cost. The populations differ though. For mu1, the population is all private colleges, and for mu2, the population is all public colleges. Other than that, the only thing that I think requires an explanation is the more than. It's going to be a more than because the entire interval is positive, and the order of subtraction was mu private minus mu public. That's how we get the more than, since that whole interval is positive. The hypothesis test example, where we have two samples of auditors. Some auditors are getting traditional classroom instruction, some are getting online instruction. We have big sample sizes this time, so we can apply the central limit theorem. Both of them are far above 30, so we're all set as far as the central limit theorem is concerned. On the previous slide, it said we were looking for evidence of a difference, so there's no specified direction, which means we need a not equal to in the alternative hypothesis. Again, I'll just use subscripts of 1s and 2s, 1 for traditional, 2 for online. The shape will be approximately normal, but we will have to use a t-distribution to compute the p-value, more specifically a t-distribution with 274 degrees of freedom, since the smaller of the two sample sizes is 275, and 275 minus 1 will give you 274. The mean is 0, because if you rephrase the null hypothesis from up above, if you subtract mu2 from both sides, you would end up with mu1 minus mu2 equals 0. And then the standard error is that root. Simplified, you end up with 0.9869 after you sub in S1, S2, N1, and N2 and simplify that, where 1 is the first row, traditional instruction, and 2 is the second row, online instruction. Computing the test statistic, since I already had the standard error, I just recycled it, so I guess I do have an intermediate step rounded off, but I think I'll be safe with that rounded to 4 places. And 1.6 is the point estimate, that's x1 bar minus x2 bar. 74.5 minus 72.9 will give you the 1.6. And then the p-value would be twice the probability of getting a difference in sample proportions of at least 1.6, which would be the same thing as twice the probability of getting a test statistic of at least 1.6212. And the doubling, just like before, is because of the two-sided alternative. So there I'm doubling a tail. There is the p-value, 274 degrees of freedom in the upper right. I have two tail checked in the upper left, and stat key only accepts the cutoff to 3 places, so I have it as 1.621, and you end up with a p-value of 0.106 because either you're doubling that right tail of 0.053 or you're adding the left and right tails together. Either way, you get the 0.106, which is greater than 0.05, the significance level, so the null hypothesis should not be rejected here.